Hi, my name is Rasmus Erlemann and I'm going to present my PhD thesis today. This PhD was done at the NTNU, Department of Mathematical Sciences, and my supervisors were Professors Henry Lindqvist and Gunnar Taraldsen. We worked on both goodness of fit testing and change point detection, and we used hypothesis testing framework in both cases. Some of the research was also done in collaboration with Professor Richard Lockhart and Rihan Yao at SFU in Vancouver. So let me present the first topic, which is goodness of fit testing. So we are given some data, we are given n data points, and we want to test if the family of distributions P is a good fit for this particular data set. So let there be IID random variables x1 to xn, and let's fix their distribution function as f. So this allows us to construct the hypothesis such that h0 is f belongs to P, and the alternative is that f doesn't belong to P. Next step is to define a test statistic, and we will denote it as V. And this measures how far the data is from P. But P is a family of distributions, so we have to fix a particular distribution from this family, and we use the maximum likelihood estimators to fix the closest distribution from this family. Some of the examples for V are empirical cumulative distribution function based, like the Cramer-von Mises test or the Kolmogorov-Smirnov test. So let's take a look at the Cramer-von Mises test statistic. So it's defined as an integral over the whole real line, and we look at the difference between the empirical cumulative distribution function of the data and the theoretical distribution function, which we have chosen from P with the maximum likelihood estimators. This is a quadratic test statistic, which means that we are squaring the distance. If we look at in the bottom, the plot, we can see the black line, which is the ECDF, and the red line, which is the theoretical distribution function. So what the integral does is it calculates the area between two curves and squares it. And this essentially gives us the test statistic value. Another test statistic is called the Kolmogorov-Smirnov test, and this works in a different way, because instead of looking at the area between two curves, we only look at the maximum distance between those two curves. So in the bottom we can see the blue line, which represents the test statistic value for this case. We also have likelihood-based test statistics, and they work in a different way. The main idea behind them is that we consider the likelihood under the null hypothesis, and we consider the likelihood under the alternative hypothesis. And we find the maximum likelihood estimators, which optimize the likelihoods. And if you look at the ratio between them, this gives us the likelihood ratio test. But sometimes the alternative hypothesis is too general. It's not specific enough. So instead of considering the whole alternative hypothesis, we consider a restriction of it. So instead of saying that f doesn't belong to P, what we can do instead is we can say that f belongs to some other specified alternative family of distributions. Like if we wanted to test if the data comes from the geometric distribution, we could test the alternative as being the type 1 discrete Weibull distribution. So it's not saying that f doesn't belong to P, but it's saying that f belongs to some other family. So once we have chosen the test statistic, we need to construct the test statistic distribution to actually calculate the p-value. So we have different methods for this. We have asymptotic methods, we have parametric bootstrapping, we can condition, and in this thesis we looked at conditioning as the main method. Once we have the distribution, we can calculate the p-value in some specific cases, as shown in the bottom. And at the end, once we have the p-value, of course we have to fix the significance level and compare the p-value that we got against the significance level. And if the p-value turns out to be lower than the significance level that we chose, we can reject the null hypothesis and say that the data does not fit this particular family of distributions that we have chosen the p to be. So let's take a look at how does conditioning work, because that's the method that we are focusing on in this thesis. So the first step is to choose a sufficient statistic. Of course, we are assuming here that the sufficient statistic actually exists, which it does in most standard cases, but there might not be a sufficient statistic, so this has to be understood. So once we have chosen the sufficient statistic under the null hypothesis, we calculate its value. So that's the small t for the particular data set that we are given. The next step is to draw a sample, the same size sample as we were given, n data points, from the conditional distribution x1 to xn, given that the sufficient statistic of them is small t, just like it was for the data set. And then we calculate the test statistic value for this newly drawn data set. We repeat steps 2 and 3 capital M times, and this constructs the Monte Carlo approximation for the distribution. So some of the good things about this method is that we don't have to do any parameter estimation, because the statistic is sufficient. We don't have to estimate the parameters like we would do with the parametric bootstrapping, for example. And this also causes the distribution to be exact, which it's not for asymptotic methods and parametric bootstrapping. And in some particular cases, it's also computationally very efficient. But it also has some bad sides. So first of all, we need conditional simulations. And this is what half of this thesis about, how to draw conditional simulations, to use those simulations in hypothesis testing to construct test statistic distributions. And the difficult part is that usually we don't have the analytical form for the conditional distribution. So we can't just use regular methods like inverse, transform, sampling, and so on. So the first paper was for the case where the underlying distribution is continuous. So let me present what we did in the first paper. So first of all, we have n continuous random variables. So we have this random vector, and we also fixed their joint PDF fx, and also their support, calligraphic x. Let there also be a function t. It doesn't have to be sufficient. This method is a bit more general, so the statistic doesn't have to be sufficient, it just has to be a function. And we wish to draw simulations from this conditional distribution of the random variables with the function of them being t. So we fix the t. Another thing that I should mention is that we are not restricted to only the IID case. So x1 to xn don't have to be IID. So this method is a bit more general than that. So our new method for drawing these simulations works such that first of all we have to choose the function chi, which depends on u, which is a vector of n components, and also theta, which is the parameter vector. And we have a couple of conditions for how to choose the function chi. So first of all, for every u and theta, the system of equations where we have applied t to this function chi has to be uniquely solvable for theta. The next condition is that for every u and theta, the function chi, its range has to contain the calligraphic x, and this has to hold for each fixed theta. And the last condition is that for every u and theta, the function chi has to be differentiable and bijective with a continuous inverse. So how do we choose it in practice? So from the first condition, we can see that the number of components in the parameter theta is the same as the dimension of t. So if t is two-dimensional, which means that the small t has two components, the dimension of theta has the same number of components. So for example, let's take a look at the gamma distribution case. So in this case, we would choose the function chi as follows. We note that we have chosen the range to be such that it's positive, because the gamma distribution has the support, which is defined on the positive real line. So the next step is that we denote the solution that always exists, which is one of the conditions. So we solve the system of equations t applied to chi, and we denote this theta hat as the solution. And it's specified for every u. So we fix a u, and there's a particular solution theta hat for this particular u. And we also have to choose a function pi, which can be a density, but we can, in more general cases, we can choose it to just be a function. So the next step, the second step, is to draw a sample u from the following density function, which in some cases is density, if pi is also density. So we have this particular function h, and we draw a sample u from this particular function. And we used the Metropolis-Hastings algorithm to draw the sample, and we found out that if we use the given data set as the initial sample, we don't have to do any burn-in with this method. So we can just basically take the second sample set that we get from the Metropolis-Hastings algorithm. We don't have to let it run for 30 iterations, for example. And the last step is to apply the function chi for this sample that we got from the function h. And we also have this solution theta hat, which is connected to the sample set u. And we put the sample and the theta hat together into the function chi, and we end up with a sample from the conditional distribution that we wished to draw simulations from. So let's take a look at how this method works in a real-life example. So we have a data set. We can see that it's a continuous data set, and it's all positive. So we would see if something like the inverse Gaussian or the gamma distribution fits this particular data set. So we need to specify the sufficient statistics for both cases and calculate their values for this data set. So that's what we have done in the bottom. The next step is to specify the test statistics. So for this particular real-life example, we have chosen some standard tests like the Anderson-Darling test, the Cramer-von Mises test, and the Kolmogorov-Smirnov test. And we use the method from the first paper to draw 10 to the power of 5 sample sets from the conditional distributions for both inverse Gaussian and gamma distribution cases. So this gives us the test statistic distribution for both cases. We also calculate the test statistic values for the actual given data set, and we compare how this test value compares in the test statistic distribution, and this gives us the p-value. So we can see that the p-values are quite small for the gamma distribution case. So if we set the significance level to be 0.05, we could reject the null hypothesis for the first two test statistics. So for the Anderson-Darling and the Cramer-von Mises tests. For the inverse Gaussian, we can see that the p-values are a bit bigger. And if we set the significance level to be 0.1, we could reject the null hypothesis for the Anderson-Darling test. But it's exactly on the level. So we would say that the inverse Gaussian fit is marginal. So even though we can't reject the null hypothesis, the fit is marginal. So if we can actually reject the null hypothesis, what it means is that we can say that the data set doesn't come from that specified family of distributions. So in the second paper, we did the same thing, or not exactly the same thing, but something similar, where we drew simulations from conditional distributions, but from discrete conditional distributions. So the main difference here is that we can actually find the analytical form of the conditional probability mass function under the null hypothesis. So let the x1 to xn be IID from a geometric distribution, and let's show how it works on this particular case. So the sum of these random variables is the sufficient statistic, and we can find the conditional probability to be as follows. So we can see that this conditional probability is uniform, but what makes it difficult to actually draw the simulations is that it's uniform on a very particular support. And the support is such that small x's, x1 to xn, have to sum to t. So we used the stars and bars concept to draw these simulations. So it works such that each sum is represented by t stars, as we can see in the figure below. So we have 8 stars, and the values x1 to xn, they mark the bars between the stars. So we put down t stars, and we put down n-1 bars, and we count how many stars are between the bars. So we can see in the example below that the first x1 is 1 because there's 1 star before the first bar. The second value x2 is 0 because there are no stars between the first bar and the second bar. The third value x3 is 3 because there are 3 stars between the second bar and third bar. And the last value is 4 because there are 4 stars after the last bar. And so how drawing the simulations actually work is that we keep the number of stars fixed, and we put down the bars in a way that the resulting distribution is uniform. Another thing that we did in the second paper is we defined new likelihood-based tests for the geometric distribution case. So we defined 3 types of tests. So first of all, we defined this test, the CR, which tests against heterogeneity in the data. Next, we defined 3 tests which use beta geometric distribution in the likelihood ratio. So if the particular data set is more skewed towards the beta geometric distribution, then these tests they perform better. And the last type is where we use type 1 discrete variable distribution in the likelihood ratio. And it turned out that this is quite versatile, especially the first one, the absolute value of SW. It turned out to be quite versatile, and it actually outperformed some of the standard tests which are supposed to be versatile, like the Cramer-von Mises test, the Anderson-Darling, and Kolmogorov-Smirnov tests. And we found this out by doing a power study for very different samples from different alternatives. So the next problem that we looked at was change point detection. So it works such that we're given a data set, n data points, and we want to know if this particular data set is IID. So if it's not IID, we say that there's a change point in the distribution at some point. So with hypothesis testing, the framework is such that suppose we have fx1 to fxn. These are the unknown cumulative distribution functions that the data actually comes from. And we choose the hypothesis such that H0 is that these distributions are all equal. And H1, the alternative, is that there exists a C such that the first C distributions are equal, then there's a change point, and the distribution changes. Fxc is not equal to fxc plus 1, and then the distribution is the same again, and they're equal again. So this index C we call the change point, and this particular model is at most one change model, AMOC model. So we're testing for just one change point, but change point detection can also be done for more general cases where we look for more than one change point. So we defined new Cramer-von Mises based tests for this particular topic. So we're given a data set, and we split this data into n-1 pairs. So first of all, we pair x1 with all the rest of the data, so x2 to xn. Next, we pair x1 and x2 to all the rest of the data, and so on until we pair the first n-1 data points just to the last data point. So for each pair, we calculate the Cramer-von Mises two-sample non-parametric test statistic. And it is defined for samples x1 to xc and xc plus 1 to xn as follows. It's actually very close to the plot that we showed in the beginning, where we calculated the area between two curves for the empirical cumulative distribution function and the theoretical distribution function. But the only difference here is that we don't compare the empirical cumulative distribution function to the theoretical distribution function, but we compare it to another empirical cumulative distribution function. So we just compare those, the first C data points, their ECDF to the ECDF of the last n minus c data points, their empirical cumulative distribution function. So based on this test statistic, we defined two tests. We've defined a summation type test, where we just sum all the possible ways we can insert the change point c together. We just sum them together. And another one is a maximal type test, where we look at the maximal value for the Wn. We look at where we vary the change point c. And we also defined the estimator for the change point through the second test statistic, Wmax. So we look at the argument that it achieved the maximal. So that gives us the estimator for the change point. We also defined, we looked at the asymptotic theory of one of the tests. So we were able to find the asymptotic distribution for the summation type test. So it works such that let us assume the change point c depends on n in a way that if n goes to infinity, then c divided by n converges to s, which is between 0 and 1. So we know that the Cramer-von Mises two-sample non-parametric test has this asymptotic distribution. So it means that Wn at c converges weakly to this series, where z, j are IID standard normal random variables. And we also show in the third paper that the summation type test converges weakly to this series, where z, j, k are IID standard normal random variables. But we can see that we have infinite number of components. So to actually numerically calculate this distribution, we have to do something about this infinite number of components. So what we did was we truncated the infinite sum and we replaced the tail by its expected value. But whenever you do something like this, you have to evaluate how does it affect the result? What's the error? So we did a simulation for various different sample sizes, and we compared the quantiles. So we compared the asymptotic quantiles to the exact quantiles. And it turns out that they are very close. So the error is relatively small. And what's more important is that the error is particularly small at the lower end. So when we look at the left plot, this is the plot for the entire quantiles from 0 to 1. And we can see that there's a slight gap at the upper end. So when the quantiles are from 0.8 to 1, there's a slight difference between the blue line and the black line. So the blue line is the exact quantiles, and the black line is the asymptotic quantiles. So if we zoom in, if you look at the right plot, we can see that the same type of behavior happens at zoomed in level. So it means that the error gets smaller and smaller as we go lower in the quantiles. So when the quantiles are between 0 and 0.05, the difference between those two curves is almost, we could say that it's negligible. And this is exactly the area that we care about the most, because if the p-value is 0.7, it's not a big thing if the error is large and the exact p-value is 0.8 or 0.6, because we can't reject the hypothesis anyway. But when the p-value is 0.05 or around that area, that's when we want the p-value to be exact and the error to be small. So these plots about quantiles show exactly that. So let's take a look at a real-life example of where we can apply these new tests. So we have two continuous data sets. We can see that these are between -2 and 3, the values. And it's very difficult to see the change point with just looking at the data sets. So we have the data set black data set, and we have the blue data set. And we calculated the test statistic values for both data sets. So for the black data set, it came out to be, the summation type test came out to be 0.696, and the maximal type test came out to be 2.106. The change point was estimated to be at 30. For the blue data set, the summation type test came out to be 0.110, and for the maximal type test, it came out to be 0.675. And the change point was estimated to be at 95. So next, we drew data sets of size n from the standard uniform distribution, and we constructed the test statistic. We can do this because this is a non-parametric test. Those tests are based on a non-parametric test. So this is the method that we can use to construct the exact distribution. And we can see that for the blue data set, if you look at the left plot, which is for the summation type test, we can see that the blue line, which represents the test value for the blue data set, is on the left of the percentiles. So it's on the left of the 90th percentile, 95th percentile, and obviously also the 99th percentile, if that's what we are interested in. But for the black data set, you can see that it's on the right side of the 90th percentile and also the 95th percentile. So it means that if we set the significance level to be 0.1 or 0.05, we can reject the null hypothesis for the black data set, but not for the blue data set. On the right, we can see the maximal type test distribution, and we have exactly the same case. So for the blue data set, it's on the left of both percentiles, and the black data set, the test statistic value, is on the right of both percentiles. So also for this test, we can reject the null hypothesis for the black data set, and we don't reject the null hypothesis for the blue data set. And that's actually very good, because these data sets were drawn from normal distribution, and the blue data set is actually IID from 0, 1 normal distribution, and on the left, the black data set has a change point at 3, and the mean changes from 0 to 1. So the first 30 data points are IID from standard normal distribution, and then the mean changes to 1, and the last 70 data points are from a normal distribution with parameters 1, 1. So it means that we were correctly found the change point for where there is a change point, and we didn't find a change point for where there's none. So it confirms that these methods work correctly. So we looked at Conditional fit testing. In the beginning, described how we used the hypothesis testing framework in that case. We talked briefly about some standard tests that are used in Conditional fit testing framework. And we also talked about conditioning for calculating the test statistic distribution. Next, we talked about the first paper, how we can use the methods that we developed in the first paper to draw simulations from continuous conditional distributions. And next, we talked about the second paper, where we developed methods for drawing simulations from discrete conditional distributions. And we also talked about the new likelihood-based tests that we defined in the second paper. At the very end, we talked about change point detection and how it's set up in hypothesis testing. And we talked about the third paper, which where we defined new Cramer-von Mises based tests, two tests, summation type test and maximal type test, and we also talked about the large sample theory for the first summation type test, and we also did a real life example. We showed how these methods work on real life sample sets. Yeah, I would like to thank everybody for listening, and this was a presentation about my PhD work. Thank you.